DeMorgan's laws. The negation of P and Q is logically equivalent to the negation of P or the negation of Q. Also, the negation of P or Q is logically equivalent to the negation of P and the negation of Q. In order to establish each of these logical equivalences, we can use truth tables as follows. We use a truth table, we construct a truth table for the statement on the left side. We also construct a truth table for the statement on the right side. When we are done with the truth tables, we compare them. When the outcomes are identical, then we have established the logical equivalence. So let's try that now. Let's establish our second DeMorgan's law. So we're going to build a truth table for this statement on the left side, and then afterwards we construct a truth table for the statement on the right side. So let's begin. So we want to construct a truth table for the negation of P or Q. Now, first, let's come up with the cases for P, Q. P, Q. Here are the cases. P is true, Q is true, or P is true, Q is false, or P is false, Q is true, or both are false. We want the truth values for the negation of P or Q. In order to obtain the truth value of the negation of P or Q, we need to know the truth value of P or Q. So we will come up with that here in the middle. We need the truth values of P or Q. And those we know by the definition of OR. True or true is true, true or false is true, false or true is true, false or false is false. Now we want the negation of that. What's the negation of true? False. Negation of true is false. Negation of true is false. Negation of false is true. Okay, now we also want the truth table for negation of P and negation of Q. Remember, that was our right side. Negation of P and negation of Q. Let's revisit that right there. Okay, so we need our cases for P, for Q. So what we need to keep in mind is that the cases that we use for P and Q must be identical to those of our first truth table, because at the end we need to compare those two truth tables. So we need true, 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 false, false, true, false, false. We're after the truth values of negation of P and negation of Q. Before we can find the truth value of this conjunction, we need to know the truth values, the individual truth values of negation P, also negation Q. So we will come up with those first. Let's do that right now. We want the truth value of the truth values of negation of P. Well, when P is true, the negation of P will be false. When P is false, the negation of P is true. Now, negation Q. When Q is true, the negation of Q is false. When Q is false, the negation of Q is true. Okay, so we're ready to obtain our outcomes for negation of P and negation of Q. So this is a conjunction, so false and false, we know is false by definition. False and true is false by definition. True and false is false. Finally, true and true by definition is true. Okay, so now let's compare. Our outcomes are identical in each case. Conclusion: these two statements are logically equivalent. So we write that. So therefore, the negation of P or Q is logically equivalent to the negation of P and the negation of Q. So therefore, we have a symbol for the word therefore in math. Okay, so the first DeMorgan's law can also be verified in the same fashion. That will be left as an exercise. DeMorgan's laws can also be established by definition, deductively. So how do we go about establishing a DeMorgan's law deductively? What we have to do is the following. Let's say we want to prove our second DeMorgan's law. So we will have to remember the definition of what it means to be logically equivalent. When are two statements logically equivalent? That means that they both have the same truth values regardless of what the atomic components are. So if the expression on the left hand side happens to be true, so is the expression that you see on the right side. If the expression on the left hand side is false, so is the expression on the right side. Then, if the expression on the right side is true, so is the expression on the left side. If the expression on the right side is false, so is the expression on the left side. So here we have a summary of that. To prove that the negation of P or Q and the negation of P and negation of Q are logically equivalent by definition, deductively, we need to show these four conditions hold. As it turns out, you can reduce the number of cases to 2. But in this particular lesson, we are not considering that yet. Okay, so let's begin. Let's try this first one here. Let's assume that the negation of P or Q is true. So assume the negation of P or Q is true. Now, here's what we want. We want to eventually establish that negation of P and negation Q happens to be true as well. Okay, so let's begin. Let's start with what happens if we remove the negation symbol. What happens to P or Q? Well, that will have to be false. This is by definition of the negation. The negation says the negation of false is true. So this P or Q has to be false. But then now what do we get from reading this? If we read that P or Q is false, that tells you that both P, Q are false themselves. So here, P is false, Q is also false. This happens to be by definition of OR, definition of the disjunction. So this is by definition of OR. Okay, what am I after? I want this statement. So I am going to have to negate P. I am going to have to negate Q. So let's do that. Negation of P, negation Q. Well, we know P is false. When we negate it, we get true. We know Q is false. When we negate it, we get true. So this result follows by definition of negation. So what next? I would like to obtain this conjunction. So let's take the conjunction of negation P, negation Q. So negation P and negation Q. Here is the calculation. True and true. That's logically equivalent to true. So that's by definition of conjunction. When you take true and true, you get true. So that's definition of conjunction. Okay, so our goal has been established. Our goal has been reached. We wanted that, we got it. So we started with negation of P or Q is true, and we concluded that the negation of P and the negation of Q is also true. Let's consider the other case. Another case is start with negation of P or Q being false. So now we assume that the negation of P or Q is logically equivalent to false. What we want this time is we want to establish that negation of P and negation Q is also false. So this is our goal right here. Okay, let's see. Let's go back in here. We have that the negation of P or Q is false. So that means P or Q must be true by definition of negation. So here we have a disjunction that is true. We know by definition of OR that in order for P or Q to be true, at least one of these, P, Q, must be true. So let's assume without loss of generality that P is the one that's true. So assume without loss of generality that P is logically equivalent to true. So since I want the negation of P, it will be false by definition of negation. Now, I want to know the truth value of negation of P and negation Q. Well, if I form that conjunction, negation P and negation Q, regardless of what the negation of Q is, regardless of the truth value of the negation of Q, the fact that the negation of P is a false statement, when I conjunct it with anything, I will still get a false result. So this happens to be the definition of AND. False and anything is still false. Okay, so this goal has been reached already. Now, when I said assume without loss of generality that P is true, you might be wondering, but what about Q? Well, if I had done the same thing with Q, let's say I didn't use P, but Q, the same argument will end up working, because all you do is you reverse the role. So now the negation Q is true, the negation of Q is false. So you have a false here. When you conjunct it with negation P, you still get false. So this right here is saying it doesn't matter which one you would choose to be true. You can choose P to be true, or you can choose Q to be true. You will still get an identical argument eventually. Okay, so that's what we just did right here. Here we have organized some steps. Previously we had done the one that have a case true leads to true. There are two cases left. We're going to leave that as an exercise for the audience. Now let's do some examples. Use DeMorgan's laws to negate the given sentence. In number 1, n is prime and less than 100. N is prime and less than 100. Okay, so question is to negate this. Our technique is the following. We're going to convert this into symbolic form. We will negate the symbolic form, use DeMorgan's law, a corresponding DeMorgan's law, to obtain an equivalent expression, and then convert it back into a verbal sentence. Okay, so let P be logically equivalent to the first component. N is prime. Let Q be logically equivalent to the second assertion, the second component. This is referring to N, so we're going to declare that N is less than 100. Okay, so here is our symbolic form. N is prime becomes P. That's and then this is Q, less than 100. N is less than 100. Okay, here's the negation of that. I want to negate, so I'm going to form the negation. The negation is going to be negation P and Q, but we know by DeMorgan's law that that is the same as the negation of P or the negation of Q. Notice that we have to switch. That was and, in the result we get or. Last step, take this and write it back in verbal format. So what is the negation of P? If I tell you n is prime, its negation is that n is not prime. So n is not prime, or n is not less than 100, or it is not less than 100. If you wanted to use mathematical symbols, it would be acceptable to write this: n is not less than 100, or you could also write that as n is greater than or equal to 100. So there could be a variety of ways of expressing that same idea. Our second example is as follows: 2, x is less or equal to 5, or x is greater than 2. We want to negate that. Okay, so let P be logically equivalent to x is less or equal to 5, Q x is greater than 2. So here's my symbolic form. P or Q, it's a negation. Well, it's going to be negation of P or Q, which is logically equivalent by DeMorgan's law to negation of P and negation Q. Now, let's see what the negation of P should be. Negation of P, what's the negation of x being less than or equal to 5? Well, it will have to be that it's not less or equal to 5. In other words, x would have to be greater than 5. Negation Q. Well, Q is x is greater than 2. The negation of it has to be that x is not greater than 2. In other words, x is less equal to 2. Okay, so now we need a negation of P, x is greater than 5, and negation Q, x is less than or equal to 2.